Okay, good afternoon everyone. I'm Sian, Loveless from the Environment Agency, and I'll be introducing your speakers this afternoon. So first of all, we've got Isabelle Daniel, who is a Professor of Earth Sciences at the Université Claude Bernard, Lyon 1. Apologies for my French accent there. And she's Dean of the Observatory of Earth Sciences and Astrophysics at Lyon. She's also chair of the Deep Energy Community at the Deep Carbon Observatory. And today she's going to be talking to us about fate and characteristics of the subsurface biosphere. Thank you.
Yeah, so we're going to go a little outside of your fields, I think, for most of you, because we've talked a lot about the subsurface and all the physics and the chemistry of the rocks, of the fluids, of the chemicals that we can have in there. But we haven't talked about our friends who are down there. So just to give you a little refreshment, and that's the brand new number of cells that have been published recently that really emphasizes the importance of the subsurface biosphere. So you and I and the visible ones, we're going to be in that kind of range in terms of cells. 3 orders of magnitude higher, 10 to the 29 cells in the ocean, about the same scale in the soil, so only 3 times. And look at this number here underground. So in the subsurface of the continents, sediments, and also the oceanic and continental sediments, and also the hard rocks in the continent. So I hope that convinces you that most of the biosphere is actually beneath our feet and is in the subsurface. And as we are talking about subsurface operations, so we should take into account those who are there, the microbes, the microorganisms who are there, and what they are doing. Just give you a number. Say, well, maybe that's not a big. That's maybe you consider it's a small, a big number, but it's at least this number is at least 1 million times the number of stars that we know in the universe. So that's actually a really big number of cells that are located underground. So underground means actually a very different environment. So that are listed here. It can go from subglacial lakes with very low cell density, groundwater and deep aquifers, sites that we've heard this morning about, so the deep coal beds or the deep bedrocks where there is some fracking or carbon dioxide injection, some oil reservoirs, and also a lot of the oceanic environments, mostly in the oceanic sediment seafloor. We don't have very reliable cell numbers when it comes to the oceanic crust, so we won't talk about those. So thanks to the recent work that was published last year by Cara Magnabosco and collaborators, and there's a lot about this in this book that was published because of thanks to the DCO, Deep Carbon Path to Prison. So I will refer a number of times to these chapters of this book. That's the most recent map of the subsea floor sediment and continental subsurface cell numbers. So you see that the highest densities are actually located on the continents, and that's where we are. The colors are not perfect, but that you can obviously see that there is a very large number of cells beneath our feet when we are located in the continents or around the world. So there are a lot of microorganisms there. So that's an important point, and we'll see how that we have to take that into account. So for those cells, so we're going to look now in terms of so we had the distribution as a function of the location per square kilometer. Now it's an inventory of the cells as a function of depth beneath the seafloor on this left panel, and beneath the continents on this on the right side. So the depth is here in the log scale. So when it comes to the seafloor, so that's the seafloor here. We are in the ocean up in the upper part of the diagram, and we're beneath the seafloor here. And here it's of course all beneath in the continents. So usually at the surface, so the cell concentrations per cubic centimeter of rocks are on the order of 10 to the 10 cells per cubic centimeters, and then there is a logarithmic decrease as a function of depth. It's more homogeneous when in the continents. There is a much larger distribution in the ocean from regions where there is always a very small number of cells, like here, those yellow points that correspond to the South Pacific gyra, where there is that's the smallest, I think, cell abundance in the ocean because of very low nutrient availability there. So, and we're going down to 10 to the minus 2, 10 to the minus 3, 10 to the 3 cells per cubic centimeter. So you won't find any numbers below approximately that kind of density because that reaches the current limits for counting, cell counting presently. So the masters in cell countings are our colleagues in Japan, and they're improving the technology for cell counting, very low cell for very low cell densities, but that's the current limit. So as these techniques is improving, so potentially the number of cells that we discover at depths and at greater depths can improve within the next years. So that's a large number of cells that are present, and I don't want us to go into too many details. So you see that there are cells that have been counted at least down to 3 kilometers depth in both cases. So there are a lot of cells down there. So the maximum, so to count the cells and thinking of how we should be taking into account this subsurface biosphere, we also need to talk about the limits of life. So let's be clear. So currently, when our colleagues, microbiologists, have been looking for life at depths, and when they've designed some expeditions at sea or went into the deepest mines that are available for scientists around the world, they've always found life. We haven't so far found a lifeless environment. So that's something also that will increase. So to do the count and to have an evaluation, we have to pose some limits for life. So the current limit for life that is known to date in terms of, we don't know the depth in terms of, depth has to be characterized in terms of pressure on one side and temperature on the other one. So pressure, we don't know if there's a limit for life in pressure. For temperature, we know that when our colleagues are doing some cultivations under extreme conditions, so the maximum temperature at which microorganisms, and that's archaea in that case, have been cultivated, it's 122 degrees Celsius. So that's the assumption for the limits of, the current assumptions for the limits of life as of today. So then this limit in terms of depth is reached, the maximum pressure or depth really depends on the geothermal gradient. So there will be a very shallow subsurface biosphere in regions where the geothermal gradient is super high. And a number of you are looking at those specific environments to get some geothermal energies. But there are also some locations, like in the subduction zones, where the temperature, the geothermal gradient is really low, and that's potentially where we could find the lowest, the deepest biosphere. Like you see those locations here in Japan, and there are a couple of very small, very deep locations that are colored here. But what are the microbes doing there? So the microorganisms, so we're talking here about mainly about bacteria and archaea. Those microorganisms can actually use the energy that is available in the subsurface using a wide range of metabolic activities. Here, that's just two examples that I've taken from the chapter by Susan Long, where she illustrates how you can start from very complicated molecules that can be available in the subsurface biosphere, and they are decomposed, and you end up with very simple molecules that can be transformed, so from CO2 to methane through the methanogenesis pathway, or then you can go to some sulfate that can end up into sulfite. So that's the sulfidogenesis. So it's just to illustrate, and there are many very complicated pathways. So if we had to put that, it would look like the Tokyo map of the Tokyo subway. So just to give you a general idea, a more general idea, maybe a simplified way of how things happen for the microorganisms at depth. There is here what we call the Redox Tower that provides a visual reference for the energy that microorganisms may generate from the transfer of electrons to each chemical species. So we tend to be up there, so we breathe, so it's basically respiration or breathing, so we are basically here breathing oxygen and releasing water. But there are a number of possibilities, and as you go down, so those are becoming less and less favorable, but still the microorganism can take advantage of it. And also in some specific environments, it costs very low energy for the microorganisms to make energy, in particular in the hydrothermal environment. So they can make a lot of molecules and maintain themselves with very little energy. But just in terms of general scheme, so as we go down, as a function of depth, the energy that's available becomes very infinitesimal. That's the same for the food. There might be some larger micromolecules, but they are pretty refractory, and it's also complicated for the microorganisms to take advantage of them. So, which means that, well, there's also a strong decrease in the cell density as a function of depth. But still, the cells are there, slower, and they've been identified. And when they are down there at great depths with low energy, low nutrient, they tend to be dormant most of the time. So very slow, as a function of that, is slower and slower and slower pace. So until they are dormant. And the goal, of course, is to maintain the microorganisms in terms of maintenance. So that means that they're not dividing. So the goal, or their motto might be, please do not divide. So no cell division. But and not like that. That's a sweet illustration that I've stolen from Wikipedia. So it's not as fast as this hand of an 8-year kid on a petri dish, so with microbes that grow super fast. So that's not going like this in the subsurface biosphere. So when the lowest, based on the measurement of the racemization of some amino acids, so some cells can divide as slow as once every 10,000 to 100,000 years. So don't ask me exactly what that means, because I think none of us can really envision what that actually means. But it's very, very low pace. But the things, even if they are dormant at depths, they can be, I can say, resuscitated. So when they receive fresh food and energy, then they can start again making good living. So that's the example of what happened on the Karpvik site in Iceland in 2012. When there's been one of the first, so Sandra can correct me if I'm wrong, I'm reporting from my colleagues at the IPG in Paris. So when one of the first carbon dioxide injection took place. So injecting carbon dioxide in the subsurface means that there's going to be some acidification of the water, a drop of pH by approximately 1, and there's going to be the dissolution of the basalt in that particular site. And then dissolution of the basalt means release of, in particular, ferrous iron and a number of cations and also some organics that have been released by many ways that I won't discuss here. But before that, and that's free food and free energy for the microorganisms. So here, that's 3 situations. So February. Just after injection and 1 and 2 months later. So at the beginning, there is a community made of aerobic to microaerobic bacteria. Here, that's the bacteria that are mostly presented. So they were living happily and developing in equilibrium or appropriately to the context. And by inducing the acidification of the medium and the release of ferrous iron and other chemicals, then the population of the microorganism changed drastically. So there's been a major decrease in terms of the diversity with the emergence of this, the beta proteobacteria. Those proteobacteria are characteristics they include actually a lot of iron oxidizing autotrophic species, and there's been also some some other iron oxidizers that were observed there. So there's a very large change in terms of the community. We can see it in a different way here. So upon injection, and I think that's important here that we look at the temperature. So we see that before reaching the 122 degrees C in terms of the limits of life, so we can go actually pretty deep. And by injecting some carbon dioxide, so that induces the dissolution of the basalt, the increase in terms of the beta proteobacteria, the development a little later of the firmicutes, and some other bacteria. So with an increase of 500 times for the biomass and a lot of potential in terms of iron oxidation. So one important point also here is that we're using all the novel techniques that are available, so the genomics, the proteomics, the transcriptomics, so we have an idea of basically who's there and what they are doing, but it's very difficult actually to take some examples and start to do some modeling in the lab, and I will talk about that in a few minutes. So there are obviously the very exquisite omics technique to see that, but that can be seen here in this SEM image of the basalt after the injection. So there's regionally the basalt, and then because of the dissolution of the iron and the bacteria that was there, so the formation of the oxidation of the ferrous iron into a ferric iron that is highly insoluble, and then some sulfur oxidizing bacteria, and then a third step with oxidizing iron bacteria. So when we want to look at this, of course, it's very difficult to select some of the microorganisms, but we can take some of those members or representatives of the genus or neuro-representative of the species, and then try to see what they are doing as a function of depth. So just as a reminder, when we talk about the microorganisms that are growing at depth, so there are a number of categories. So we start with those that are very happy at ambient conditions and which growth decreases immediately as pressure increases. We have the piezo-tolerant, so those are piezo-sensitive, the piezo-tolerant, they grow perfectly until over a small range of pressure, and then it decreases rapidly. We have the piezophile, and then the hyperpiezophiles that do not grow at all under ambient pressure. So to try to address who's down there, so we can do some sampling, and also that's what we did last year in Iceland. We can leave the samples on the pressure, so there are now vessels to do that, and we can bring those samples and transfer them under pressure for some cultivation, and try actually to do the cultivation of the microorganisms who are there. It's very difficult, but we're working on that. And then measure their microbial activity as a function of pressure. So that's what we do in particular in Lyon. So when it comes to measuring redox changes in molecular compounds, then we do Raman spectroscopy as a function of pressure. When we are looking at dissimilatory metal reduction, then we can use X-ray absorption spectroscopy, and then we can see what's going on as a function of pressure. That's what we did with one cousin of the iron, the sulfur oxidizer that has been found in the Carpix site, so the Thiobacillus thioparus, so that oxidizes sodium thiosulfate. So in some specific diamond, not on diamond envy cells here, it's sapphire envy cells. And just to give you an idea how that works, so we start with the Thiobacillus. We provide the Thiobacillus with thiosulfate, and then monitor the transformation of the thiosulfate into sulfate as a function of time at a given pressure. And then we can see when that stops as a function of pressure. So here that's a function of time. And here when you take the endpoint, you see that this Thiobacillus is perfectly happy and works until 30-35 bars. So which means that the activity in terms of sulfur processing under those conditions may happily happen until 300 meters depth, which is corresponds here in that particular case. So that's an example of how we can proceed with those microorganisms. So identify who's there, what are they doing, and in particular during the subsurface energy operations. So there's always an induction, a disturbance of the environment, and then even if you assume that there's no cells and temperature is in the 50 degrees C, there is necessarily some cells that are present there, and by adding new nutrients, new energy to those microorganisms, they can start working again, for the best in some cases and for the worst in some others. And that says I would like to thank our colleagues from Reykjavik Energy and all the team when we did the sampling. That was very interesting, and that was really the first time that we did some this pressure sampling that allowed then a number of other opportunities. Thank you.
That was fascinating. Thank you very much. Do you have any questions?
It's been far from
Yeah. Well, I have a question. If no, oh no, we do. We've got a question over there. No, after you.
Isabelle, thank you very much. The first slide, when you show those number of cells, is that different types of cells?
Different.
Like this one here, you said 10 to the 30 cells underground.
Yes. Yes.
So is it total number of cells, or is it different?
No, that's the total number of cells as we know it as of today.
All right. That's a lot.
That's a lot, yes. It's a million times more than the number of stars we know.
So for the effect of pressure, does that matter? Because it probably equalizes, right, after a while. But this, in terms of, you said that the activity stops after your last.
Yes, on that particular strain. So it really depends on the microorganisms. One point so I mentioned it briefly, but I said that there are a very small number of species that are cultivated today compared to the huge biodiversity. But it's even worse when we're talking about the subsurface. Looking at the piezophilic microorganisms or hyperpiezophilic ones, the number of strains and species that are currently cultivated is less than 50. So we have very little understanding of the activity of the microorganisms there in terms of so when we try to do the work in the lab. The way it's assessed currently, it's really collecting some samples, filtering when it's possible, increasing the number of cells that are available, and then doing all the genomics, metagenomics, metatranscriptomics, and also the proteomics to have an idea of what's in there. But it's always some small fragments of the pieces. So what we're trying to do on the other way is to improve our capability of doing some cultivation under half pressure, having more representative of this subsurface biosphere, and then try to do some direct measurements when they are fed again with really high energy and nutrients.
I'll move us on there if that's all right, and we can ask you some more questions and a discussion at the end. Okay. So next we have Erik Nicol from the Petroleum Technology Research Centre. Erik is responsible for the management and delivery of enhanced oil recovery research programmes, and also manages the centre's carbon capture and storage programme, which includes the Aquistore and Wavern projects. Today he'll be talking about lessons learned from long-term monitoring of wells in Saskatchewan and the Aquistore project. So, thank you, Erik.
Thank you very much. Thank you very much to the organizers, Colleen and Alberto, for inviting me to come all this way to tell you about our projects that we have going on. I guess we're in some ways a little further down the line in the development of CCS project, and in other ways, maybe a little bit behind. It's kind of an interesting talk. I'm going to talk about Wavern and Aquistore. Wavern was a project that if you were students in the mid-2000s in this field, you would have definitely heard about. It's what led us to do the Aquistore program. So I'll give you a bit of background on that, the site characterization, and then some of the MMV that we've done around that, but also what we call public assurance monitoring. So to ensure that we have the public assurance to do what we are doing. And obviously lessons learned not only in the technical realm, but in the public awareness realm as well, and try to do it all in 15 minutes. So here we go. Wavern. Wavern was a CCS project that was started by a company called Pan-Canadian. They were planning to take CO2 from a coal gasification plant in Beulah, North Dakota, inject it into the Midale Formation, which is right here in the geologic column in order to enhance oil recovery. They did start that in 1998 and have been injecting ever since to a total now of almost 40 million tons. We studied the heck out of Wavern as one of the sort of proto-projects for CCS. We were able to do some of the original things like 4D seismic for the use of monitoring plume conformance and things like that. Volumes have been written on Wavern. The expertise that we gained in Wavern we applied to Aquistore. Now what is Aquistore? It's obviously a lot deeper. We're injecting into the Cambrian Deadwood Formation, or the lowermost formation. I'll talk a little bit more about that. But the CO2 comes from a coal-fired power generation facility. This is called Boundary Dam. The dam it's not a hydroelectric dam. The dam is there to provide a reservoir that you see behind the plant for cooling. The plant has, I guess, 6 units. 1 and 2 are on this. They're decommissioned. 3 is not spewing any smoke because it's got the CCS. 4, 5, and 6 are to be decommissioned by 2022. So BD3, what happened here? Well, Boundary Dam 3, about 160 megawatts of this. The entire facility is about 800 megawatts. Here you could see this sort of line coming here. This is the flue gas came here, and this is the capture plant right here. All of the magic happens in this side, and this is where the compression happens. A lot of what goes on at a capture facility is compression. In a map view, here's the power plant. It goes off to this point via pipeline for sale off to what I mentioned before, Wavern, the Wavern field. They're still taking all the CO2 they can get and injecting it in a monitored way. The rest of it comes down to this little pair of wells here that on this map is called the Sask Power Injection Well Site. That's what we know as Aquistore. Aquistore takes the remaining 500 to 1,000 tons per day of CO2 and injects it permanently in a deep saline aquifer. So why is a guy from Saskatchewan, of all places, hard to say, easy to draw though, it's a rectangle in the middle of Canada. Why am I here? Why am I the expert in this? To think I'm an expert in anything is crazy, but CCS in Saskatchewan works really well because we have a lot of those pink dots, which are high emitters. We have a lot of that green area, which is good injectable area for this kind of stuff. And if you want to know how big of an area that is, there's the UK sitting inside our little square of a province. So it's thousands and thousands of kilometers of suitable rock formation for injection. The Deadwood Formation, I can't sit here in the birthplace of the science of geology without talking a little bit about the Deadwood Formation. It is a Cambrian formation that sits basically unconformably upon the crystalline basement with these sort of highs that stick up between it. It's a mixed, or it's a siliciclastic variegated shale and sandstone formation with sort of streaks of porosity where we are at least. It gets a little bit more pure porosity to the west and the mountainous areas here in Alberta. Zooming in a little bit, I don't think there's a scale on this, but each of these squares are townships, and those are 10 kilometers, each one of those squares. Our wells are down here in this green spot with a thickness of about 120 to 140 meters of deadwood, or so we had hoped. Before we drilled it, our only other wells were up here, and we had one down here in the United States. Control to look at the deadwood when it's at a depth of 3,000 plus meters is not good. And we had these areas where it was known to be zero thickness. Interesting scientific problem, but becomes a pretty major problem when you're about to spend $20 million on a couple of wells. But the wells were drilled, and we had about 160 meters of deadwood there. But the deadwood we found to be a challenging environment. It's about 100 to 120 degrees Celsius. Geothermal, we do have geothermal projects in the area, one starting up very soon. More importantly, though, is the salinity. This red area here denotes salinity of greater than 300,000 ppm, or 30%. Very challenging water. If we were to ever bring it up and cool it even a few degrees, it would turn into piles of salt. How this is going to affect geothermal activity? Negatively, is what I would say. This is what the country looks like around there. It's big, and it's flat, and it's sunny, even in winter when it's minus 30 degrees. The local residents include farmers and lots of cows, and this is the drilling rig drilling the well in the summer of 2012. It's a pair of wells, an injection well here, going through all of these formations here on the left to a depth of about 3.4 meters. Open hole completed, or it's cased to total depth, and then open hole completed here with a packer and an injection string of tubing right to the bottom, 3.5 kilometers. 150 meters away to the north is just a plain well that we use for monitoring. On the outside of casing, there are 2 fiber optic lines to measure both seismic activities, temperature, and pressure. There's also the ability for fluid sampling to sample fluid from the formation on the outside of casing. The well itself, though, is sealed off from the formation, and we use that to hang geophone strings down to monitor seismicity as well. One of the things that we sold this project on was that it was going to be an MMV field laboratory, measurement, monitoring, and verification. We will measure the plume, any possible deformation around the place, any leakage, obviously, into the biosphere, and lots of in situ monitoring to inform injection operations, such as downhole pressure in real time and that kind of thing. We proudly say that we've had 0 measurable impact on soil gas, 0 impact on groundwater, and no measurable seismic activity. We've had downhole geophone strings that can measure down to a -2 scale with nothing reported. Makes you wonder if they're working at all, but they are. They're measuring earthquakes in Bolivia and other seismically active areas. They're just not measuring anything right in the immediate vicinity of us. So what else do we have for monitoring? Well, it's a 5.5 kilometer square that we monitor around the 2 wells here right in the middle. There's 630, in a 2.5 kilometer square, there's 630 permanently installed geophones. So we use them for seismic monitoring or seismic imaging, but also there's a certain number of those that are kept on all the time to measure for seismic activities related to injection. That's what these are here. The green squares, they're a little hard to see. Those are all the sites where we measure soil gas, not only the absolute soil gas, but the flux of the soil gas as well. And then we have these monitoring superstations that have things like INSAR reflectors, GPS coordinate locators, tilt meters, and piezometer wells for measurement, or for water level measuring, and also the content of the water. And this was the original seismic sections that we shot in order to get an idea. So, just to keep this moving quickly, we've measured seismically the plume. We can image it from 36,000 tons injected here, right up to 141,000 tons injected a couple of years ago. We've measured a plume. Here's the 2 wells that seems to be growing in a very distinct way. We've also measured the same thing, though, using DAS. DAS is something you'll hear about. It's distributed acoustic sensing on a fiber optic line. So instead of all these expensive geophones that need constant upkeep and maintenance, we can bury a DAS line or 2 in the ground and put one along a well and measure almost the same thing with a little bit worse signal-to-noise ratio. So this is one of the things that we've found. Also, from a sort of a sideways or a cross-sectional view, we can see seismically the zone of injection is injecting as expected, backed up by repeat seismic or repeat PND logging, pulse neutron density logging, in the observation well. So there's lots of these little things that we're doing to make sure that we have conformance of this CO2 underground. This is just another way of looking at it, not only through seismic amplitude, but looking at the impedances. Same result. We're seeing a nice growing plume there. It's a challenge, though. The challenge is that the plant itself is one of the first of its kind. And it was told to me once that by a smart guy who said that the limits on injection usually don't have anything to do with the geology or the well or anything. It has to do with the compressor. A compressor is a really sensitive piece of equipment that costs a lot of money, and without it, you're done. And they break down a lot. And so as a result, we have an injection profile here in blue, injection rate, that is incredibly up and down and up and down and down for long periods and up and going. Lately, it's been a little bit better, but that's a very irregular injection profile. And now tell that to a reservoir engineer who's trying to history match some other aspect of injection. It's a challenge, to put it mildly. The red is injection pressure, and we see sort of differences between the injection rate and the pressure. They're not completely compatible, as one might expect. We have to slowly ramp up injection pressure, or else it sort of seems to want to block us off. Lots of funny little things here. Also, with our temperature, this rainbow-looking thing here is a profile of temperature going down. Remember I said we had those fiber optic lines all the way down. At a normal injection time, you sort of get this regular pattern of hotter as you get deeper. But then in periods where there's more injection, everything gets moved down and we cool off the well to a degree. Cooling of the well, or cooling of the reservoir, more importantly, well, that has some problems associated with it. Remember the 30% salt. You cool it down a liquid with 30% salt in it, we get some precipitates. You hit a 120 degree formation with 60 degree CO2, you change the geomechanical properties such that you decrease the minimum fracture pressure. So have we fractured this well? Probably not, but it's possible. So lots of questions that we didn't think would come up are coming up now, and we are fortunately still able to learn and find solutions to these problems before this technology gets rolled out full scale across places like Europe. Putting this all together, we've obviously done models. You do models for everything. We have on the left, Schlumberger builds a model for just for the regulatory requirement. In the middle, the EERC in the United States, one of their important laboratories, looked at the seismic and built us a model based on that. The University of Alberta is taking into account these temperature changes when we do a simulation and all of the challenges that come with that. So modeling is a very important thing, I think, at the end, when you have streams of data and you want to put it all together in ways that make sense and ways that you can look at the relationships between different data sets. Modeling is ideal for that. Monitoring. So we're going to talk about what we've learned from monitoring. This chart, you can't really, this is all the different monitoring technologies here. This is the volume of CO2 injected. The only point I want to make here is sometimes monitoring is a regularly scheduled thing, like this, along here. That is, P&D logging, for example. Sometimes it happens just based on the injected CO2 volume. We have a plan to do another seismic monitor at 250,000 tons, which we've just hit, so it's happening next month. The previous one was at 141. We set these arbitrarily, not based on time, but based on injected volume. So monitoring programs aren't always just time-based. Also developing minimum data sets. Research in North America where this science has moved along and where pilots are moving towards regular industrial operations. This is that original long list of monitoring. Do we want to maybe take it down a little bit? We are assessing what is the most useful for the price and trying to get that price down. And then even further, where there might only be a few things, if we were to do this again, would we have the full, what we call a Cadillac system? Cadillac meaning a very nice car in North America that would maybe be the Rolls Royce of monitoring systems here instead of the Cortina or something like that version that is much less expensive. And again, here's those three things: the soil gas, the water, and the seismic. We spend millions of dollars monitoring these things, and we know that they always show 0. So, are they necessary? Well, that gets us into the point of public assurance. If we're spending millions to provide public assurance by doing testing that we know will be 0, is there a better way to convey public assurance to people than by doing that? So these are following is some slides given to me by my communications department. One of the purposes of effective CCS communications is to provide the clear scientific detail where it's needed. This means that, and I've seen a little bit of that here this morning, that images should be to scale. So this is from a famous documentary called Gasland, where it talked about the evils of fracking and all of that stuff, and it showed the fractures going up to what looks like about 10 feet from an aquifer. Is that the right way to present it with reference not only to fracking or to CCS, or is something like this image I showed before? That's the power plant there to scale with how deep it is, the purple being the area of injection. Simple things like that can really change the conversation, make people realize, oh, there's a lot of different intervening formations and rock formations that are impermeable between the CO2 and me. Wording. We talked a little bit about the type of words. They matter. If we're going to plug and abandon a well, we're going to abandon it. Does that mean we're going to walk away from it? When CO2 is not only critical, but it's super critical. You and I and everyone in this room knows that supercritical is an area on a phase chart, but to someone who doesn't know that, something that's supercritical sounds super dangerous, right? So these are the sorts of things that we have to have in mind. In the end, what we want it to be is a story, a good story about what we're planning to do. Alarmed and concerned what does it say here? The alarmed and concerned trust scientists and scientific organizations, whereas the doubtful and dismissive are more likely to talk to their family members or find anecdotal evidence about it. Proper project communication puts the science within a context of stories, and this is the important part, that we need to have a story. So tell us a story. All right. Well, here is the story of Aquistore on a day that we had a communications event for the local public in Estevan, Saskatchewan, which is a town of about 15,000 or so people interested in what's going on underneath their town. You could walk in and get the whole story from introduction, what CCS looks like around the world, subsurface and seismic, what does that look like? Here's what the injection wells are going to look like. Here's how we're going to measure it all. And here's what the capture plant looks like. So all of these people came in, walked around, got the whole story from us, and hopefully went away with greater knowledge. And if they were to talk to someone else, they would say, you know what, I think those guys know what they're doing. I think it's going to be safe. It's really deep down there. So lessons learned from all of this. The management and dissemination of data, that comes from me as a project manager, getting data to the people who need it and at the time that they need it. Geological data often comes first, but people often want that all through the project and don't give the geologists any time to work on that. I'm a geologist by training, by the way, so I feel for those guys. Project integration between researchers, kind of in the same vein. When you have, we all know the jokes between geologists and engineers about how to get them to work together, but in this case it's crucial. And then you throw geophysicists into the mix and it becomes even more difficult. Missing the basics for the sake of cutting edge work. Often we want to do the most cutting edge stuff that we can think of. But what's the permeability of our reservoir? Oops, we didn't take good measurements of that, you know. Well, it's variable, okay, but how variable, you know? Missing the basics because we wanted to do whatever the latest and greatest was. And then finally, rethinking monitoring and how much is required to create the public assurance and the actual assurance. I'm a scientist, I don't want to see this thing leak. And I know that we don't do this just so that the uninformed public will think we know what we're doing. I want to do it on a basis that is real. So that I can stand up here and say confidently that the chances of a leak are incredibly minimal. All of these findings and a lot of stuff on Wavern can be found on our website, or you can order these books or send me an email, ask for my card after. We've published a lot on this and continue to with Aquistore as well. Finally, I'd like to thank my Science and Engineering Research Committee. These scientists, without them, there wouldn't be a PTRC in the CCS. And this guy, he was my field assistant one day while I was checking some monitoring wells or monitoring systems. And if he's a local resident, yeah, the local residents seem to be doing okay. Thank you very much.
just have one very quick question. Yeah, just one very quick question, and then we'll move on to the next speaker.
When you say rethinking the monitoring, what do you mean? Is it in terms of sensors? Is it in terms of frequency? Is it in terms of strategy or?
Yes, all of those. Mostly it comes down to cost, though. We costed this, and it was millions of dollars in monitoring. If CCS is to roll out across the world in the way that we think, maybe some of us think it should in order to help combat climate change, we're going to have to figure out the monitoring systems that work the best and provide the most information for the least amount of money, and still provide that public assurance that's so important. Thank you.
And finally, we have Michele Barbier, who is an ethics expert for the European Commission and has recently founded the Institute for Science and Ethics, who aims to develop ethical approaches in science and innovation to improve environmental and social issues at the global level. So today she's going to be talking about S4CE ethical recommendations.
So I want your book. With pleasure. Okay, so in fact, I jumped into the project Science for Clean Energy very recently by meeting Benedict Menez, and we discussed, and I met some of you already to see if we can work on some ethical recommendation from Science for Clean Energy. So why should we talk about ethics? Maybe because on a philosophical point of view, in the 70s, this German philosopher, Hans Jonas, was really worried with the deployment of new technologies that was arising in the 70s. And he wanted to think about the responsibility to provide an answer to the problems posed by these technologies. And he was specifically focusing on environmental issues and genetic engineering issues. So today, we enter the Anthropocene era. So it means that our planet is contaminated, is impacted, and it is our responsibility to protect our resources, our environment, to develop actions in order to become the steward of our planets. And we need to move for a paradigm, to move for a new global management approach. So this responsibility starts with everyone, scientists, industry, policymakers, and the society. And as the scientists, we need to provide the best knowledge, develop trusting relationships, be honest and fair, optimize, share, respect cultural diversity, animal welfare when necessary, and protect the environment and build capacity. And this is what I wish to develop with this consortium, is to provide ethical recommendation with you experts. So, I will just review the context, but you all know that we have this energy demand increasing over the years, and we are supported to develop and to find new clean energy in order to stop with this old fuel basic energy. In Science for Clean Energy, we focus on these four topics, which is the carbon capture and storage, enhanced oil and gas recovery, geothermal energy, and shale and tight gas production. We have already identified some challenges, so maybe I will switch some words, but it's not only technological or environmental with the risk of pollution or gaseous emission, it's also about conflict, public, industry. It's about importation. We do not produce, but we import. It's about storage for economical reasons and not for scientific or environmental reasons. So it's all about the different challenges that we know, but we can extend and think about. So we have more and more use of the Earth subsurface. You all know these different conventional, unconventional techniques. And some of them induce anthropogenic seismicity. You are all experts in this, so I will not give you a course on this, but Stanislav Lazowski gave me these slides, and you know that there are anthropogenic seismicity risk, and I think I will ask Jorge to provide me with these slides on these different actions to implement when we face different level of risk of seismicity. So because we have this anthropogenic seismicity, we are facing, and you are facing, this societal acceptability and these terms that not in my backyard. So this is typical in different industrial sectors. So as an example, you know, in Germany that regarding the carbon capture and storage, there was some really strong pressure. There was, I think, a lack of trust. It is true also for the shale gas exploitation. What is interesting also about fracking is that we are in Europe, but we do not have the same legislation. It's all different, and Andreas told me 2 days ago that the shale fracking was banned. So it's interesting to see also that we have the legislation, the public perception, the industry, the scientists, and of course the policymakers that are all involved in these different perceptions. We need also to think on a global scale, because here if we see the different nice location for potential carbonation, mineral carbonation sites, but if we look at our map, world map based on the gross domestic product, you see that northern countries are a little bit more wealthier than southern countries. So we have to be careful when we say no in my backyard to not displace the problem, the issue, and goes to other countries that maybe have the resources but do not have the same means or way of protecting their own resources or their benefits. So it's really important to think globally. And we need also the economy because we need this clean energy, we need an economy to live, but we really need to find a good way, a good balance in between the economy, the environment, and at the global scale. So in fact, based on all those different points, and I did not present all the work we are currently doing, we try to give some recommendations. Here are only few examples. As it was said before, we need really to be transparent when we communicate to and with the civil society. We need to use the right scientific terms and to be as more as possible understandable. We need to really engage a discussion right from the beginning and not wait until we have an issue to discuss with local population. We really need to start the discussion right from the beginning. And the good news is that we are moving towards a new mode of governance these days, because you look at the COP21 in Paris, you look at the United Nations Sustainable Development Goals, they are all based on different exchange from different type of participant or steward from the earth. It's about science, it's about society, it's about the industry, it's about policymakers. And policymakers are waiting for your advice as scientists. So we really need to give them some input in order for them to take the right decision. We need to reinvent or to reinforce the trust between politics and us, between us and the society, between us and the industry and the public. And I took this from this company is a company developing artificial intelligence, but I really think that this trust If we are trustworthy, reliable, understandable, secure, and teachable, it means that we can really reinstore a dialogue. Of course, we can talk also about when we have an event, what can cause an event and what an event can cause. So not think about only one aspect of the impact, but try to think more globally and think about this multi-risk assessment. Risk assessment, multi-risk assessment, life cycle assessment are part also of this overall process. And Andreas gave already a presentation, so I would not detail, but this is something we will include in our recommendation. It's about also access to data. It's really important to have a maximum of data. We need data in order to anticipate potential or to monitor potential seismic activities. We need data to model. We need data. We really need to have access to all these data. So I know sometimes it's not easy from the private sector because there is an ownership and there is competition, but as scientists, we really need to put the data into public access as soon as possible because it's really, really, really helpful. And the data have to be of good quality. They have to be accurate. They have to be interoperable because this is another concept, fair. The data needs to be findable, accessible, interoperable, sorry for my accent, reusable. And I think if we all apply this concept, then we can really push to have a good development, a sustainable development. So these are only the few ideas that we will develop in the ethical recommendation. There are many more, and if some of you want to participate, so you see the spirit, please contact me. We are drafting. It's a matter of you are the experts, you have your opinion, your experience, you had to face in the past some challenges, and maybe you got some solution, you got some ideas, maybe you do not, but it's not about a matter of saying we have to do this. It's really some kind of recommendation. And the recommendations are towards the scientists through a publication, but we wish to contact also policymakers. Like I was asking this gentleman from the European Commission if he knows somewhat the European Parliament, because the information has to go also at the higher level. It's also a matter of transferring this information to the industry. And of course, these are all the colleagues from the Science for Clean Energy project who are cooperating in this project. You're welcome to contact me if you want to contribute and to propose something new. Okay.
Do we have any questions? Great.
Yep.
Hi, I was wondering if you think there's enough conversation currently between scientists and policymakers, and if there isn't, how might that be kind of promoted in the future? Because it seems that a lot of the time the scientists saying one thing, but it isn't really reflected in policy.
That is right, that is not always easy, and I had the example of your colleague from the Environment Agency was saying we keep saying to the policymakers some point of view and they would not take into account. It's a matter of pushing, maybe by using different channels. The industry, the economy is sometimes a channel that policymakers might listen more than scientists. So I really think if we build something strong and a good communication, and we can try, I'm not naive, I don't think we will change the world, but almost if we can change the way how we work and to be really focusing on finding solutions instead of each of us going his own way and his own process. So, but I know it's a challenge.
Have we got any other questions? Okay, well, if we invite everyone up now for a discussion together, all the speakers from this afternoon. Okay, so questions for anyone, I think, bearing in mind the topic of this discussion. Okay.
Hi, great talks, everyone. Really enjoyed it. You talk about engagement with the public and effective engagement and effective development of ethics. How do you measure whether you've actually had an impact or been effective in what you've been trying to do? Sorry, I'm a scientist. I like measuring things.
Yeah, no, you're right. I will think about. We'll find out some indicators. I think, okay, I do not know how to measure. I know how to proceed. Then, you know, I started this approach only 1 year ago, so I think we need a longer time scale to have some feedback. I can already see how scientists within a project will start to invite the society, NGOs, or policymakers. I just constate right now that we have more and more this type of consultation, even at the United Nations. So we can imagine, actually, I will look for, that's a good idea, for indicators of, I will. Good point.
I would add that there is communication research ongoing in things like scouring social media, counting the negative comments on a particular issue. As a scientist right now, I don't know that there's a lot of quantification of it, but you get the sense that if there's a picture of a guy with a gas mask and CO2, you're doing something wrong.
That's a good point.
Okay, next question, Eve.
I guess my question goes to Erik along the lines of the monitoring. Mm-hmm. To what extent did you consult with the community about what sort of things they wanted to be monitored, and how much did that inform the sorts of things you're going to do? And presumably getting to that idea about social license and whether you're going to have people protesting at the gates, if they're involved in the process, that presumably will mean that that's satisfying some of the questions they have, or at least they're getting involved in the dialogue to learn about the processes involved.
That day that I showed there was well in advance of drilling any wells. So it was a two-way communication that day, I would say. But more specifically with respect to that project, we were in an area that was very oil active, and the local community was very accustomed to the types of things that we were going to be doing, from injection of fluid. It just happened to be CO2 instead of salt water or acid gas or something that normally goes on there, or just to drilling a well, what a drilling rig looks like, and what results from the presence of a drilling rig. Most of the local residents were familiar with that, but you are right in that if we were in an area where onshore drilling was not common, involving them in the process as early as possible to determine what's important to them, just as you said, but it comes down to the biosphere, the water, the soil, and they don't want to be feeling any earthquakes. That's for sure.
Can I follow up that? So what role did the local regulators have in terms of mediating that interaction and also setting the ground rules?
Not in our case, not a lot, actually. They set the rules for injection, and they ensure that we follow them. But beyond that, it seems as though the bulk of the interaction between us, whether it's a research group or an oil company, is left to that company. Because if there is a outcry against something that you're doing, I guess it's your own fault.
Just as I'm dominating this conversation, but I guess in the social license to operate, I guess, research area, at least from Australia where I'm from, there's some increasing evidence that the public's perception of the amount of governance and oversight is actually really important in terms of mediating, I guess, their trust in terms of, and so, which goes counter to lots of industries, I guess, want to do things themselves and to interact to control the interactions. And so it's that public perception that there's basically an umpire that or referee, somebody's keeping industry in check is actually really important for for moderating the levels of trust.
I agree. But being Western Canada, there's that independent streak in everyone out there, that's for sure. And it would certainly be different in Europe, I'm sure.
Oh, I wonder if we could ask our other two panellists what they think about how that would apply in Europe and social license to operate. Yeah, if you've got.
So, okay, the question is, how would we develop the same type of approach in Europe?
So do you believe that monitoring is required in Europe in order to operate and have people on board and provide that social license?
Okay, I think in the different countries, anyway, the legislation would be different. Either for the exploitation, for the exploration, and probably the monitoring will also come with the legislation, what will be mandatory and what is not mandatory. So first we need to set up already to list what are the different legislation, and maybe goes to the European, what I was thinking, European Parliament or some other to highlight the need or not, what are the minimum indicators we should monitor and why not. Because I do not think at the moment we have something transversal. It's each country has its own, from what I understand.
Okay, thank you. Any more questions?
Process.
This is kind of a follow-on question for Erik, I think. You've obviously done a lot of monitoring over a long period of time, and you're in a community that already understands something about this. If you were to go, I don't know, 10 miles, 100 miles away to do this again, do you think you'd be able to make a case to a new community that the same level of monitoring isn't required because it proved in the other project not to be that necessary? Or do you think you would never be able to get that argument won in a new community?
10 or 100 kilometers away, yes, but if it was 1,000 kilometers away in a completely different part of Canada, it would be much more difficult. So to your point, yes, it would be more difficult. There is a lot of geological information available in the area that we're doing. So these sites sort of select themselves by the virtue of how much geological or other information is available about them. If I was to go to Quebec, for example, where there's almost no oil wells or gas wells drilled, and I had no idea, I wouldn't be able to speak authoritatively on it. So no, we wouldn't be able to do less monitoring there. But in an area where there is a lot of information and a lot of data about what the rocks are like there, and about what the geological container can do there, I could make that claim. So it is very site-specific, I suppose.
You think you'd be able to make that claim to a non-geological audience?
Exactly.
You would? Okay.
Yeah.
Thanks.
I have a question for Erik. Do you monitor the biological activity, or did you think about?
So the soil gas, a lot of the CO2 that they measure in soil gas is from biological activity, and it has a specific isotopic signature. So I guess we are measuring it in that way. We can tell biologically derived CO2 in the soil gas from something that's injected very easily. But other than that, no, there isn't a specific measurement of microbes in the soil or anything like that.
One of the difficulties with technology or other proposals is that people have already made up their mind, and often very, very early on. Mm-hmm. So I wondered what proportion of the population, say in your area, were there to be influenced in the first place. There were probably lots of no's, lots of yeses. What's the bit in between that you can actually influence?
Yeah, I mean, I've heard it's 40, 40, 80 or something like that. 40% are on your side no matter what. 40% are going to be against you no matter what, and 20% maybe in the middle. For what we're trying to do in the area that we're trying to do it, it was probably much more in our favor, just because of the long history of the oil industry there, and there hasn't been major catastrophes in our area, basically in Western Canada, as far as gigantic pipeline spills or oil well blowouts that affect a lot of population. It's also, as you saw, a very sparsely populated area. So it's not in anyone's backyard, really. So that's a lot of favorable aspects that we have going for it. When you speak to shale gas in Pennsylvania or New York, that's much more densely populated. I'm not familiar with the specifics around it, but I can understand the outcry against it just because these things are going on right where people live. So there's all kinds of factors to consider in that. And it comes back to the question, if I was to do this somewhere else, would we take a different approach? Well, we probably would have to, I think.
Thank you. Isabelle, those microbe guys, obviously when we are drilling and injecting, we are perturbing an environment. My take from what you've presented is that the reservoir of this thing is so large that the perturbation that we do is really insignificant. Is that the case, or we don't know yet? We're still studying what's going on.
Well, I think that you're correct. It's probably infinitesimal on the global scale, but on the specific site that is in operation, it can induce some dramatic changes. So like clogging of the wells or inducing some massive dissolution of some rocks. So that can induce some really important changes. The population can really change from 1 week to the next one. Because the diversity, so we need to always remember, so in the subsurface there's still a very high microbial diversity. So most of the microbes at great depths are dormant. But if there are some, if you provide them, I can say it in a different way. So if you provide them free lunch, then they're going to be extremely happy. So some of them are going to be extremely happy, depending on the perturbation that is induced by the injection or by the operation that is made. So that's introducing basically some new energy sources that were not available before or in small amount. And in that case, that the community is likely to react very quickly.
I mean, I noticed that there were some processes that could turn CO2 to methane with these guys. Could we put them to work?
Yes. Yes, it does.
Any other questions?
We were talking about oversight and governance. To what extent is it important that the oversight and governance organization is seen to be independent of the organization that's running the plant? I mean, normally, it's the plant operator who provides the monitoring data that someone else looks at.
Yeah.
Would it be better if it was the other way around, that the plant operator was taxed in some way and that money was then spent completely independently to monitor their activities?
That's kind of what is being proposed in Canada with a carbon tax right now. In our specific case, SaskPower, who own the plant and the wells, they're a Crown corporation, so they are part of the government as well. So the only arm's length organization involved in the whole thing was us, I guess. And so you're right in that that can potentially be seen as just kind of an incestuous kind of relationship between everything. Especially when it gets political as to who is in political power. I should mention in Canada, the natural resources are managed by each provincial government and not the federal government in so much. The federal government looks at transportation of natural resources across boundaries, but within Saskatchewan or within Alberta, it is the provincial government, and those change every 4 years or every few years. And it is good to have an external body looking at this, which is, in our case, the Ministry of Energy and Resources, who have guidelines to do this on.
But it's still the company themselves creating the monitoring data. Should you have a completely independent monitoring organization?
Right, that would just do it completely beyond arm's length, just completely independently. I suppose to a degree that's what we provide. We are partially government funded. We have no specific masters in government that we answer to. So I guess we are that third party. It did come to light in, and it's a separate talk that I kind of wish I would have had some slides on today. During Wavern in about 2006, there was an allegation by a farmer of a leak of CO2 into his dugout or pond, as we call it. And he was claiming it was killing his animals and this kind of thing. And the Sierra Defense Fund or Eco-Justice sent some lawyers, and you know, it got a lot of press and did a lot of damage to CCS. We stepped in and provided the third-party data to show that no, this was in fact not injected CO2 isotopically based on carbon isotopes and other tracers. Definitively showed that it was not the case, that this was a leak, and everything kind of ended, but not before it did a lot of damage to the science as a whole, I would say. So we were seen as the third party at that point between not only the government, but also from the company who would, Pan-Canadian or Cenovus at the time, who also did their own studies and found there to be no connection, but what is their word worth in the general public compared to ours, I suppose. And that was an example of that.
Okay.
I was wondering if I could bounce back the same question to the Environment Agency to see what is the situation in the UK. And just before, I also wanted to ask to Isabelle, since there are all these microbes that can do many different things, is there a protocol that industry or academia should do? Say we select a site for CO2 storage. Do we need to do something to know what are the microbes living there before we start operations, just not mess up everything?
Yes, I think that there should be we should go for an inventory before starting. That's something that is pretty standard, and that could prove to be very highly valuable for future operations in any case. So, and it's not just about the surface, the soils. It's as deep as the drilling is done, and I think that would actually be much better for the community in terms of the worries, the concerns that people are talking about, and when we know who's there and how they can react, because we can also do some modeling. So when we know who's there, we can also do some modeling upon injection or upon changes of the environmental, what's going to happen, and if it's favorable or unfavorable to future operations. So it has various number of interests.
Yeah, and it's a source of business. It's biotechnology, and it can be also interesting for another type of economy to develop and to grow these guys in order to degrade hydrocarbons or whatever hydrocarbons.
I can't dodge this one, can I? So going back to your question about the Environment Agency, and so, I mean, the biggest efforts that has gone into monitoring is obviously around the shale gas sites in the UK. The operators are required to carry out the monitoring. They tend to have consultants, so they wouldn't necessarily do it themselves, but they tend to have a consultant to do it. But the British Geological Survey have obviously been funded to carry out quite extensive monitoring around those sites as well. So currently they are being monitored quite extensively, both close to the well site and a little bit further away as well. Whether or not it should be a tax that means that either a regulator or someone else undertakes that monitoring that's a bit more arm's length, well, I don't know. Whether or not it would be feasible, I mean, that would require quite a lot of people to do. But like I say, the British Geological Survey are doing that kind of work already as well, to be that independent monitor, basically. Yeah.
As a former survey geologist myself, I approve.
And we had a question here.
Okay, you'll have to bear with me because I'm completely unfamiliar with the topic area, but it is a question for Isabelle. You may have said it, but you were saying how we can impact the formation of the bacteria for better. Gentleman suggested about them over there. But and then you said also for the worse. What's an example of for the worse?
Well, so in terms of operation, so in the case, for instance, of the carbon dioxide injection, so stimulating the local community and developing some of the communities because of the generation of ferrous iron that can provide energy to the bacteria through disseminatory metal reduction. Then it induced an increase in the biomass by 500 times. So that's actually a lot, and that can actually induce clogging of the wells. So then, of course, there can be some issues with that. But in some other cases, so you could, and that's not an example that I have, but could facilitate actually the dissolution of some minerals and then increase the porosity and the permeability of the rock. So that would be like the best situation. So that's why I think that having an inventory of the microbial community before operations could be actually highly valuable in many different ways.
We've got any more questions? I have one for Isabelle, if that's okay. So I've heard people talk about with mine water geothermal, which is obviously a lot shallower than what we've been talking about today, but that the microbes can actually create the heat within the mines and actually produce a bit more of a resource than you would get naturally. Is that something that is feasible? Can the microbes create more of a resource there for us?
Yeah, well, they can make many different chemicals. So in terms of heat, maybe that would require a lot of microbes, and I'm not sure also that correspond in terms of temperature range. I'm not sure that they can be engineered in the temperature range we're interested for geothermal operations. But they can produce some added value, for instance. Yeah, definitely.
Thank you. Okay. Any last question? No? Okay, well, thank you to all our panel today and for your fantastic talk.